Okay, so here I'm going to make a video on my iPad going over all the main topics that we discussed for forces in motion. So basically, I'm going to go through the outline that I posted on Google Classroom, which is just a combination of all the outlines from all the classworks throughout the unit. And as I go through the outline, I'm going to highlight some of the most important ideas that you need to know for the test, and then going over some example problems to help you understand what's going on. So I'm going to try to go through this as quickly as I can to make it, as efficient as possible. All right, so first things first, we talked about motion. We talked about ideas like position, speed, direction, acceleration, velocity, and we use these quantities in order to do calculations. So, going over the very first outline, motion is relative. So what this means is that basically there has to be some reference point, right? So when we're saying we're moving, it has to be with respect to some other thing, right? So typically we say we move with respect to the surface of the earth. That's like the default reference frame. And yeah, that's really all there is to it. Speed is distance over time. You should already know that from other math classes, and you've probably covered it before in other science classes. Very simple equation. It's distance divided by time. And then here you can see that you can rearrange that to see your total distance covered, right? So if you know your average speed and you know for how long you're traveling, you can figure out your total distance. Really straightforward. Just to make sure you understand the units, it's measured in meters per second. That's the SI base unit. But you could also use miles per hour or kilometers per hour. It's all the same idea. You have some unit of distance divided by some unit of time. Velocity is directed speed. So basically, the main difference is that velocity is a vector, whereas speed is a scalar. All right, so make sure you know what vectors and scalars are. So remember that a vector has direction and magnitude. Okay. Okay, and it can be represented by an arrow. Okay, so say we have some velocity vector v. Okay, and it's some velocity at a given direction. So say I'm going 10 meters per second to the right. Right. So that's a velocity vector because I have some magnitude and I have a direction. Scalar only has direction. I'm sorry, I misspoke. It only has magnitude. No direction. So this is stuff like mass, volume, temperature. These are things that you don't specify that there's a direction, okay? Whereas vectors are quantities that have direction and magnitude. All right, so make sure you know that. So velocity is a vector because you have to specify the direction. Acceleration is also a vector because, again, you're specifying the direction. So something you need to know about acceleration is that it's basically change in velocity over time, right? So it's your change in velocity over time. All right, so you need to know that. So it's the rate at which velocity is changing. It's important to note that just basically whether or not you're speeding up, slowing down, or technically changing directions, you don't have to worry about that. But it's the rate at which your velocity is changing, right? So, for example, the acceleration due to gravity on Earth is 10 meters per second squared, right? So what that basically means is that as you're falling, your velocity is going to change at a rate of 10 meters per second, right? So you're going to be speeding up as you fall through the air. Let's see, what else is there? Okay, how far and how fast? So we do need to know these equations. Okay, so let's talk about how fast. Okay, and that equation is V is equal to A times T. Okay, so this is your velocity, this is your acceleration, this is your time. All right, you can use G instead of A if you're talking about gravity, right? So, in terms of gravity on Earth, right, the free fall acceleration is 10 meters per second squared. Okay, so say you want to see how far or how fast something's falling after a given amount of time. Let's just do a quick example. Say you drop a boulder, right? So you're standing on the side of a cliff. And here, actually, let's make that a little bit closer here. Okay, and you have a ball, and this is going to be at t equals 0. Okay, so you're going to drop the ball, and it's going to fall down. Okay, and as it's falling, we're going to see how it speeds up over time, right? So we drop the ball, or this rock in this case, so drop rock. Okay, and let's see here. So same scenario, except at some later time. All right, so now say the rock is over here. Okay, and this is at t equals 2 seconds. Okay, so how fast is it falling? Right, so right when you drop it, the velocity of the rock is 0, right? Because you're holding in your hands, and like the instantaneous moment that you drop the rock, it's still at 0. It has to speed up. But as it's falling, it's going to speed up, right? Because that's how gravity works. And you can calculate how fast just by using the equation. So after 2 seconds, 2 seconds of free fall. Okay, let's actually use the equation. V is equal to a times t. The a in this case, the acceleration, that's just gravity, right, which is 10 meters per second squared. So we have 10 meters per second squared times 2 seconds. And it's obviously, it's pretty easy, right? So 10 times 2, 20. 20 meters per second, all right? And if you fall for 3 seconds, you're going to be going 30 meters per second, 4 seconds, 40 meters per second. You get the idea. This is part of the reason we use 10 for gravity. Technically, the gravity on Earth is 9.8, but 10 is close enough, right? You're only 2% off, and it makes it way easier to calculate, right? You don't need a calculator. You can just use 10. You're going to be close enough, and it makes these problems a lot easier to understand and deal with. So let's keep going. How far? Now let's look at some examples using the how far equation. So let's do the same scenario, right? So say you drop the rock off the cliff. Okay, now we're looking at how far, right? So the rock's in the hand. This is at t equals 0. So obviously it hasn't fallen yet. But at some later time, t, let's see. So now we're at the cliff, and it's fallen for, say, 2 seconds. Okay, so now the rock's over here. This is at t equals 2 seconds. Okay, and now we're asking how far did it fall, right? So what's this distance here? How far? Okay, well, the equation for how far is d is equal to 1/2 at squared. All right, so assuming you drop it from rest, you can just use this equation, right? So I'm at the edge of a cliff. I drop the rock for 2 seconds. How far did it fall after 2 seconds? Well, just plug in the values. Now, don't forget you have to square the time, okay? And you have to multiply the acceleration by 1/2. So we have 1/2 times the acceleration, which, again, we're going to use 10 for gravity on Earth, just because it's easy to calculate with. So 1/2 times 10 times the time squared. Okay, so 2 seconds, that's how long it's been falling for, but we have to square it. All right, so when you do all the math, you have 1/2 times 10 is 5 times 2 squared, right? So remember, you have to do the 2 squared first, okay? So 2 squared is 4. 4 times 5, that comes out to 20 meters. All right. Again, double check your math. If you want to use a I mean, for me, this doesn't seem like it's all that difficult, but, I can understand that, you want to double check and make sure that you're not messing up the order of operations. Don't do 5 times 2 and then square that value, because that's technically not correct. Square the time first. Okay, so whatever the time is, square it, and then you're going to multiply by the rest. You also need to know how to rearrange the equations, right? So say you needed to solve for time, or I told you, I drop a rock and, it hits the ground after a certain amount of time, or you know how tall the cliff is, and you need to figure out how long it's going to take to actually hit the ground, right? You just have to rearrange the equation. So say we had 1/2 at squared, and if you need to solve for t, then you have to rearrange the equation. So here I can multiply both sides by 2. So I get 2d is equal to at squared. Divide both sides by a. Okay, so I have 2d divided by a is equal to t squared. And then finally, you take the square root of both sides, right? So square root of 2d divided by a, right? So I think we've done that before when we measured reaction time. We had to actually use the equation to figure out what the reaction time was, right? So if you know how far something's going to fall using a meter stick, you can then solve for the time just by rearranging the equation. Either way, just remember how far and how fast, okay? So these are the equations. How fast? Okay, V equals AT is how fast. Oh, I have it up here. Okay, and then you have how far is T is equal to 1/2 AT squared. You're going to have an equation sheet, so you don't have to memorize those equations. Okay, so graphs of motion. Make sure you understand that on a speed versus time graph, the slope represents acceleration. And then on a distance versus time graph, the slope represents the velocity, right? So let's look at these two equations, or at least these two graphs, right? So let's say we have a position time graph. Okay. And let's say we're looking at an object that's moving at 5 meters per second. Okay, so say we have some object that has some velocity 5 meters per second. Okay, and if we look at the graph here, we have the position with respect to time. Okay, and then say, you know, at 0 seconds, it's going to travel 0 meters. All right, but then let's look at what happens after it drops 1 second. Okay, so after 1 second, it's going to fall 5 meters. Okay, so this is going to be measured in meters. This is measured in seconds. Okay, at 2 seconds, it's going to fall 10 meters. At 3 seconds, it's going to fall 15 meters. All right, so here, let me make some space for that. So 15 meters, right? And this is position in meters. Okay, so here we have 15. And here, let's make a different color here. All right, and then that slope is the velocity of the object. Okay, so you need to know that. Okay, so the slope of position time graph to position time graph is velocity, right? Or distance time graph, right? However you want to think of it. A position time graph, the slope's velocity, or the distance time graph, the slope's the speed. But it makes sense if you really think about it, because slope is rise over run, right? So if you look at the graph here, your rise is going to be some measure measured in meters, right? So you're going to have your distance measured in meters, or your position measured in meters, and it's going to be over time, which is measured in seconds. So you have something that represents meters per second. That's going to be the velocity. Okay, so for a position time graph, the slope is the velocity, right? So slope position time graph is velocity. And then for acceleration time graph, I'm sorry, not acceleration time graph. For a velocity time graph, the slope is the acceleration, right? So the let's actually do an example with a velocity time graph. All right, so this is a velocity time graph. And let's say this is for an object that is in free fall. Okay, so we have an object falling down, and it's going to speed up as it's falling down. So say we have here, you know, at 0 seconds, it's going at 0, and then every single second, it's going to speed up 10 meters per second. 3, 4, okay. So after 1 second, you have an object that's in free fall. It's then going to be going 10 meters per second. At 2 seconds, it's going to be going 20. Right, at 3 seconds, it's going to be going 30, and then we have 40. Okay, and that's the idea. All right, so being able to read a graph and understand what's being measured. Right, so let's see. Here we have the slope, in this case, is going to be the acceleration. All right, so the slope of velocity time graph is acceleration. And again, this makes sense because just looking at what slope is, right? So slope is rise over run. Here, the rise is some velocity in meters per second. So you have meters per second divided by seconds, and you know, you're going to end up with meters per second squared. So that's going to be a unit of acceleration. Okay. So in this case, the acceleration is equal to 10 meters per second squared, which is the slope. And then here, in this case, for this problem, we had a velocity of 5 meters per second, right? So that's the slope of this graph. So yeah, just make sure you know those basic motion graphs. Okay, so projectile motion, we talked about vectors and scalars. So something else to note, the perpendicular components of a vector are independent. So the reason why that's important is because in projectile motion, the horizontal velocity actually isn't affected by gravity. Okay, so say I have some object, right? So let's look at projectile motion. Okay, so for projectile motion, the only thing that actually changes is the vertical velocity. The horizontal velocity doesn't change. Okay, so say I have some object here, and I look at its velocity over time. Okay, so actually here, let me do, I'll use green for horizontal velocity. Okay, so let's say this is the horizontal velocity, Vx. Okay, at all the different points, Vx doesn't change, right? So say I have some point over here, Vx isn't going to change. But Vy will change, right? So here I'll do, for Vy, I'll make it red. So this is your velocity in the y direction, okay? So I throw an object up, the velocity in the x direction is not going to change because there's no acceleration in the x direction, but the velocity in the y direction will change, right? So here at the very top, Vy is 0, okay? And then at the bottom here, Vy is going to be going the other way, right? And that's basically what gravity affects, right? So gravity, it goes down towards the surface of the Earth or the center of the Earth. So it actually only affects the vertical velocity because the perpendicular components of vectors don't affect each other, right? So the horizontal velocity is unchanged, and the vertical velocity changes due to gravity, right? So actually, I'll write that down. So Vy changes due to gravity, right? So remember, gravity is the acceleration that all objects in, free fall, they accelerate at a rate of 10 meters per second per second. So obviously that's going to change your vertical velocity, but your horizontal velocity doesn't change, right? So Vx doesn't change. Right? And that's the basic idea. The reason why is because there's no horizontal acceleration, right? So the acceleration in the x direction is 0, and the acceleration in the y direction is 10 meters per second squared going down. Okay, that's the basic idea. All right, let's see here. So Newton's first law. All right, so I'll just write down all of Newton's laws, or at least how to remember them. Right, so the way to think of Newton's first law is the law of inertia. Okay, so this is the law of inertia, right? Basically, objects in motion want to stay in motion, and objects at rest want to stay at rest, unless there's a net force, right? So if you have a net force acting on something, its motion will change. Otherwise, its motion is going to want to stay constant, okay? So one thing that's important to note, or at least a common misconception with Newton's first law, is the fact that an object moving at constant speed, there's no net force acting on it, right? So if you're moving at a constant speed, right, you're in motion, you're staying in motion, your motion's not changing, that means there's no net force acting on you. Okay, so that's something that's important to note. That's a very common misconception, is that people think that an object has to have forces in order to keep moving. And it's not true. You can have an object moving in outer space where there's no forces acting on it, right? So you don't worry about gravity or anything else. You just have an object moving in a straight line. Its motion is not going to change because there's no forces acting on it. The second law is F equals ma. So this is important to know, or at least how to use, right? So Newton's second law is F net is equal to ma. Okay, so the net force, not only is it the sum of the forces acting on an object, but it's also the equal to the mass times acceleration of the object. So here, let's do an example here. So let's say we have a box and we have some forces on it. Okay. So say we have a box here and I have a bunch of forces acting on the box. Okay. Say I got, here, I'll use different colors. I'll use green and red. Okay. So say I got 30 newtons pushing the box forward, but then I have 10 newtons pushing back on the box, right? 10 newtons going the other way. Okay, and let's say the box has a mass of, let's say 5 kilograms. So the mass is 5 kilograms. Okay, so using these equations, how do I find the acceleration of the box? So find acceleration of box. Okay, here, let me. Okay, so first you need to find the net force, right? So the net force is equal to the sum of the forces, right? So this is what's nice about drawing a free body diagram, is you look at all the forces acting on an object. If the forces are all balanced out, then you don't have a net force, and the object's motion is not going to change. It won't accelerate because the net force is 0. But in this case, obviously, the forces are not balanced. I have 30 newtons going to the right. I have 10 newtons going to the left. So I end up with a net force of 20 newtons going to the right. So my net force here is 20 newtons to the right. Okay, so don't just blindly add them up. You have to consider the direction. Okay, so if I had 10 newtons and 30 newtons going in the same direction, then yeah, it'd be 40 newtons going in that direction. But because the 10 newtons is going against the 30 newtons, right, the 10 newtons are going to the left, you can consider that to be negative, right? So say you want to call going to the right positive, then going to the left would be negative, and you end up with 30 minus 10, and you end up with a net force of 20 newtons to the right. So now that we have the net force, let's find the acceleration. All right, so I know that F net is equal to ma. Okay, so if I rearrange this equation, I have F net divided by m. All right, so here we have 20 newtons divided by 5 kilograms. That was the mass of the box, and you get 4 meters per second squared. Okay, to the right. So that's the acceleration of the box. Okay, so this is a classic example of using Newton's second law. You look at all the forces acting on an object, and once you know what the net force is, you can use that to calculate the acceleration. You could also work backwards. If I told you what the mass of the object was, what the acceleration was on of the object, then you would immediately know what the net force is. Okay, so let's see here. Okay, so friction. So we got to talk about friction. So friction resists motion. That's one way to think about it. So say you have some, this helps you in terms of identifying the direction that friction goes in. But say you have someone sliding on the floor, right? And there's some coefficient of friction between the object and the floor, and you need to calculate the force of friction. So here's the equation. Again, it's going to be on the equation sheet, so you don't need to memorize it, but you need to know how to use it. So force of friction is equal to the coefficient of friction times normal force. All right, and again, normal force is the forces in between surfaces, right? So say I have here, here actually I'll write it like this. So force friction is equal to the coefficient of friction times normal force. Okay. So let's say we had an object that has a mass of like 10 kilograms. Okay, so let's say here we have some object. The mass is equal to 10 kilograms, and it's resting on the floor. Okay, and we need to figure out what the friction force is acting on this object, right? So let's say this object is sliding on the ground and slowing down due to friction. Okay, and let's say the coefficient of friction is given. This is based on what the surfaces are. So let's say the coefficient of friction is 0.3. Okay, so that's the coefficient of friction, and we need to calculate the force of friction. So calculate the force of friction. Well, first things first, let's draw a free body diagram to figure out what's going on. So here we have the box, and there's actually going to be 3 forces acting on the box. So here I have the weight force, right? So force of gravity, that's pulling it down. I'm going to have a normal force that's holding it up. Okay, so that's the normal force between the ground and the box. And then I'm going to have a force of friction that's going to be slowing it down. Okay, so force of friction. Okay, so, you know, something that's important to note is this box is going to be accelerating, right? It's going to be slowing down. Okay, so that's going to be some acceleration going to the left, but it's not going to be accelerating up or down. Okay, so in this case, it's not like going up in the air or falling through the ground. The forces have to be balanced in the y direction. All right, so just note, generally speaking, the normal force is equal to the force of gravity. Okay, if you have a thing resting on the ground. Now, that's not always true. You can have things like inclined planes. You could be on an elevator where you're accelerating up or accelerating down. We're not going to deal with those problems for now, just because it gets more complicated, and we want to just go over the main ideas, right, the concepts. So here in this case, say the mass is 10 kilograms. Oh, that's one thing that's important. I didn't mention weight. So you have to know how to find the weight of an object. Remember that weight is mass times the acceleration due to gravity. Okay. And that's what the force of gravity essentially is, right? So all objects accelerate down at a rate of 10 meters per second squared on planet Earth, but their actual weight, the actual force of gravity that's pulling them down, you have to take the mass times that acceleration due to gravity. All right, so say we have here the mass, I think I already wrote it, was 10 kilograms. All right, so 10 kilograms, then the weight would equal the 10 kilograms times the acceleration due to gravity, right? So we're going to say 10 meters per second squared, so 100 newtons. Okay, that's the weight. And that's also the normal force, right? So the normal force is going to equal 100 newtons because the forces have to be balanced in the y direction. All right, so the vertical forces are balanced in this case. All right, so now finally we can calculate friction. So we have normal force, right? So we have normal force, we have the coefficient of friction. All right, now we can calculate what the force of friction is. So the force of friction, in this case, we have a normal force of we have a coefficient of friction of 0.2, no, I said 0.3. So 0.3 times a normal force of 100 newtons. Okay, so we get a force of friction of 30 newtons, right? And you can specify going to the left, right? So if this object's sliding to the right, friction's going to be going to the left because it's slowing down. Okay, so that's the answer to that problem. Pressure, we're not going to have any questions on pressure for the test. Free fall, okay, air resistance. One thing that's important to know for air resistance, so usually you neglect air resistance in most of your problems, and we're going to specify. So you have something that's in free fall, and we don't have to worry about air resistance. I'll let you know in the problem. But there are certain cases where, just the idea of what terminal velocity is. So in real life, right, not in a idealized physics problem, but in real life, as things fall, the air pushing up on the object is going to increase as the object speeds up, right? So basically air resistance depends on the frontal area, and it depends on the velocity of the object. So there's this point where you reach what's called terminal velocity, where your air resistance equals the force of gravity, right? So the force of air has to equal the force of gravity. Okay, and that's terminal velocity, basically. So force of air. So your acceleration becomes 0, right? Your net force is 0. If these two things are balanced, as soon as the force of the air equals the force of gravity pulling you down, then your net force becomes 0. You're no longer accelerating. that's your terminal velocity, right? It's effectively your max speed, right, as you're falling through the air. Okay, so Newton's third law. All right, that's something that's important to know. Action, reaction. All right, so Newton's third law. Action, reaction. And this one's pretty simple, as long as you follow the rule. Basically, that you just flip the nouns, right? So if you have an interaction between two objects, okay, the reaction, right? So the action is force of A on B, right? So force of A on B, that's the action. The reaction is force of B on A. Okay, so let's say I have it like this. Here's B, okay? So the force of, here, actually, let me use different colors. Okay, so here on object B, there's going to be some force pushing it. I'm going to say that's the force of A on B. Okay, that's the action. And then the reaction is going to be the force of B on A. All right, so the force of B on A. All right, and that's what Newton's third law essentially states, right? So the force of A on B, okay, is equal and opposite to the force of B on A. Right, so mathematically you would say negative because it's going the other way. All right, and that's Newton's third law. But to keep it simple, say you have a hammer hit a nail, right? So that was on the Kahoot, right? So the action is hammer hits nail. The reaction is nail hits hammer. Okay, and those forces are equal. So the force of the hammer hitting the nail is equal and opposite to the force of the nail hitting the hammer. All right, so all forces come in pairs. That's just how it is, right? That's how any interaction occurs. You have two objects acting on each other, and those forces are equal and opposite when they interact with one another. And yeah, just flip the nouns. You'll never mess up, okay? So if, so for example, boulder falls to earth, okay? The action is earth pulls boulder. The reaction is boulder pulls earth, okay? Or say you're dealing with a normal force, okay? So the table pushes the book up, okay? Then the reaction is that the book pushes the table down, okay? So, I mean, that really is all there is to it. Don't overthink it. Now, another thing that's important is action reaction on different masses. So you have the same force, okay? But the thing is the objects will interact in a different way. Okay, so for example, I think this is another one on Kahoot that some people got wrong, was a bicycle and a car. So a bicycle hits a car, which object experiences a greater force? So they actually both experience the same force, because that's Newton's third law, action reaction. So the force of the car on the bicycle is equal and opposite to the force of the bicycle on the car. But obviously the bicycle is going to, it's going to hurt the bicycle more or less, right? So whoever's on the bicycle is going to be, in bigger trouble, because the thing is the forces are the same, but the masses are different, right? So let's say the force was 1,000 newtons, okay? 1,000 newtons on a bicycle is going to accelerate it a lot more than 1,000 newtons on a car, right? So 1,000 newtons acting on a car, it's not going to accelerate very much because it's a lot more massive than the bicycle. So that's really I think that's the part that tricks people the most with action reaction, is that, they overthink it in terms of like acceleration, right? So yeah, they're going to accelerate if you have different objects of different masses. If they have the same force, right, they're going to have different accelerations because they have different masses. So that's something here to put down. So don't forget that F equals ma, right? So F equals ma. So if you want to calculate the acceleration, right, that's F over m. All right. Another example, say you have a bug hitting a car, okay? And the bug is the one that, goes splat. And the reason for that is because, well, they're going to have the same force, equal and opposite forces, but the force of the collision is going to affect the bug a lot more than the car. Because even, let's say the force is just 1 Newton. Well, the bug has hardly any mass, right? Say it has a mass of 1 gram. So then its acceleration is going to be like 1,000 meters per second squared. So it's practically going to explode, right? It's going to go splat. Whereas 1 Newton acting on a car is like nothing, right? Because a car has a lot of mass. So 1 Newton divided by, 1,000 kilograms, that's hardly any acceleration. It's essentially 0. So anyways, that's pretty much it. A recap. of everything that we covered. We talked about vectors and scalars, motion, velocity, acceleration, position, stuff like that. How fast and how far. All right, so you need to know those equations. They're going to be on the equation sheet. Also the motion graphs, right? So position time graph, velocity time graph. For projectile motion, understanding that it's a combination of constant velocity, horizontal motion, right? So you have some horizontal motion that doesn't change, but then you have this vertical motion that is changing because of gravity, right? And then when you look at it, it comes out to look like a parabola. And then for Newton's laws, we have the first law, second law, third law, and then we had some examples, right? For second law, obviously this one has like the most examples associated with it because it deals with free body diagrams, the sum of the forces, F net equals ma, friction, right? So that should be pretty much it, right? So yeah, hopefully after reading through all this and all the review that we've done, you'll be successful on the exam.